It's a unit of length you get from the three fundamental constants by using dimensional analysis. All right. Now we'll need this fact, this background fact, right here. This multinomial coefficient, by Stirling's formula, is roughly equal to this, to first order in the exponent. And this is precisely equal to e to the n entropy of the proportions. So if I wanted to maximize the number of configurations, well, if I wanted to know how many sequences there are with these occupancy numbers, n1 through nk, it's e to the nh. Now, here we go. Now, there were no atoms in 1872, although people toyed with the idea that there might be some. No one had ever seen one. You had to worry that if you couldn't turn lead into gold, that maybe there were such things as lead atoms and gold atoms, but that's another story. Mach, as recently as 1895, said, "I don't believe in atoms." So that's where things were at that time. All right, now Boltzmann, by looking at the behavior of atoms, the billiard ball atom model with elastic collisions, I was able to explain pressure, temperature, and entropy by putting them forth, giving them concrete interpretations in terms of perfect gas. So let's see how he went about it. It's a major breakthrough. All right. We have a large number of atoms in a gas, and velocity. A given atom has coordinates x, y, z of position, and velocities vx, vy, and vz in those directions. Now we ask, coarse grain the space, and so I is x, y, z, v, and, position and velocity within epsilon. That's the cell. And n sub I is the number of atoms in that cell. Now we're going to ask how those number of atoms move, and whether or not the entropy, which we'll soon define, increases or not. So there are Ni particles in cell I. Now let's look at the collisions. We have some particles, we know the position and velocity of these, and they're n sub j with this position and velocity. And when they collide, some of the particles, let's look at a single collision that ends up in K and L. Position and velocity after the collision. You know how to do it, of course. It's conservation of energy, and conservation of momentum, I think, is enough to give it to you. Now let's postulate the collisions per unit time between molecules in this position velocity and this one. And let's say it's Bijkl. So a given molecule in I and J will sort of go to KL with this probability. And so N is the number of molecules, so this is sort of like the expected flow of IJ into KL. Notice if I double the number of particles in Ni, I double the number of particles flowing into KL. So thus the rate of change of molecules in state I is given by this quantity. The number flowing out of flowing into IJ from KL minus the number flowing out, summed over all J, K, and L. Great. So now we go to the next step. We'll make one more assumption, that there's microscopic reversibility. If two molecules hit like this and go like that, if I reverse the time, they would hit like this and end up like that. That amounts to saying this propensity going from IJ to KL is the same as going from KL to IJ. And the flow just depends on how many particles there are in IJ, K, and L. So then the rate of change of particles that are in cell I is given by this quantity here. And now it's time to look at the entropy. So, what Boltzmann looked at was the multinomial coefficient, n choose n1 through n sub m, the cell occupancy frequency. And he said, you know, how many configurations are consistent with n1, with the n sub i's? And he wanted to show that you go from a low entropy state to a high entropy state. That you go from a state that has many, has very few configurations, N1 to one that has many. Now, because of the equivalence of the log of the multinomial coefficient and the entropy, this is the same as saying you go from a high entropy state to a low entropy to a high entropy state, and that's what he's trying to prove. So there you go. So the entropy is summation Ni log Ni, which is the critical. If you know that, you know the entropy, you know everything. And the summation of the number of particles over the number of states is n. So there are n total particles. Now let's find the rate of change of the entropy. Well, that's summation. First, the derivative of n sub I. N sub I dot log n sub I. Plus n sub I times the derivative of log n sub I, which is 1 over n sub I. But look, summation of n sub I equals n, which is a constant. So if I take derivative of both sides, which I've done here, I get 0. So that term disappears. So now I'm only interested in this. And from the previous transparency, that's equal to this quantity. Has to do with the flow in and out of states I, J, K, and L. Now we notice an interesting thing. This involves I, J, K, L. This only involves log Ni. So let's write down a similar expression, which is equal, where we look at the index J, and another where we look at K, another where we look at L. They're the same expression. They're all equal. So let's add them up and divide by 4. So convince yourself that that's true. And now you have summation of this times x minus y log y minus x, log y minus log x. But this, by elementary calculus, is always negative. So therefore this derivative is negative, and you've proved Boltzmann's H dot system, that entropy increases. Oh, incidentally, the entropy, he talked about minus the entropy and so on, not to be confused. It goes in the right direction. By the way, I have a criticism. So Boltzmann says you go from a low occupant state configuration N1 to a higher one. The flow is that way automatically if you have microscopic reversibility. But if you look at it, there's implicit Markov. Like when I went into cell I, if I knew what cells I were in before, then I would know what subset of cell I'm in. I'd have a finer view than I get from just the coarse graining that I imposed on it. So indeed, but all of these equations just assume that it didn't matter how I got into cell I and J, that that's all there is to know. And the calculation went at force. So in a way, Boltzmann's theorem only applies to Markov processes, ones in which I forget everything except for the gross, gross quantization, the cell. By the way, there's a quantum version of this, which I won't go through. Weakly interacting dilute gas, the entropy is that. Eigenstates, Boltzmann, Fermi Dirac, average number of transitions. This is looking familiar there. Principle of micro reversibility at the bottom. Familiar. And that allows you to show that the entropy increases. So now let's back off Boltzmann's work and see what's going on. Is entropy increase true of all Markov processes? And we've already examined this question. Does the entropy in the future behave like the entropy? Well, oh, here it is, looking back in time. That is, the present given the n, a symbol n in the future, or n in the future given the present.